Have you ever wondered why you put salt on the roads in winter? Well, you may know that the salt helps to melt the ice. But why does this happen? Well, it all has to do with solutions and what are known as colligative properties. Well, what are colligative properties? Colligative properties are changes in a solvent's physical properties due to the presence of a solute. So we're going to look at two different colligative properties. The first one is freezing point depression. And what this means is the higher the concentration of solute, the lower the freezing point of the solvent. For example, water usually freezes at 0 degrees Celsius, but by adding salt to that water, or ice as we do in the winter, the freezing point drops to maybe -5 degrees Celsius. This means that instead of the ice melting only when it's above 0 degrees Celsius, the ice can start melting once the air temperature gets above -5 degrees Celsius. Therefore, the ice will begin to melt much sooner. But why does this happen? Let's look at this simulation from PHET of water freezing. So we're going to start with water in a gas state, and we're going to cool it down. So as we cool it down, the molecules move closer and closer together. They're no longer able to move fast enough to avoid the intermolecular forces, and they form a crystal structure. When we introduce a solute to this, the solute particles get in between these water molecules. And if we have solute particles blocking these water molecules from moving together, they're going to prevent the water from freezing. Therefore, it has to be much colder for a solid to form. Let's look at this on a smaller level. So here are water molecules, and what happens when we introduce salt? Well, when we introduce the sodium chloride, remember that ionic compounds break apart in water. Look what happens. This ion that's dissolved prevents the water molecules around it from coming closer together. And here we can see several ions. So if we have many of these ions dissolved in water, we prevent more of the water molecules from coming close. If you can't have close solvent molecules, you're not going to form a solid. Therefore, lower temperatures are needed to stop the particles from moving. This also leads into the second colligative property we're going to talk about, and this is boiling point elevation. Now we see how these ions block the particles, water molecules, from coming together, but what also happens? Well, there's a force, there's an attractive force between the ion and the water. There are intermolecular forces. In this case, it's the ion dipole force. If we put the sugar in the water, it would be the dipole-dipole force and hydrogen bonds. But there's a force that holds the water molecules together with the solute. If there wasn't an intermolecular force, then the substance wouldn't dissolve very well. So the second Colligative property is boiling point elevation. And this is the higher the concentration of the solute, the higher the boiling point. Of the solvent. And we'll look at the water example again. Water normally boils at 100 degrees Celsius. But if you add sodium chloride or some other solute, maybe you can raise the temperature to 103 degrees Celsius. So now the water will have to be hotter before it can start to boil. To look at this from the molecular point of view, we'll start with our water in the solid form, and then we're going to heat it up. But remember, we have solute particles that are in between these water molecules. And there's an attractive force between these particles. So when we heat up the water to make it start to boil, we actually have to reach a higher temperature, because all these molecules are being held by those intermolecular forces until finally we get to a high enough temperature, which is going to be above the normal boiling point of water, where the water can finally evaporate or boil. It's actually very simple to calculate what the change in boiling point or freezing point is going to be for a given amount of solute. For freezing point, the equation is delta TF, meaning the change in freezing point, equals I KF times M. So what do these variables mean? Well, we said delta TF is just the change in temperature, the freezing point. I, or lowercase I, is the number of particles that a substance breaks into when dissolved in water. For example, if you dissolved glucose in water, I would equal 1, because glucose is a molecular compound, so it's not going to break apart. It stays together as a molecule. But if you were to put sodium chloride in water, I would equal 2, because sodium chloride, when placed in water, splits up into aqueous sodium and aqueous chloride ions. The equation for the glucose would be like that, just going solid to aqueous. If I add calcium chloride, CaCl2, I would equal 3. And this is actually why a lot of the salts used on the road are calcium chloride or something similar, because the bigger I is, the bigger the delta T is, the change in temperature. So calcium chloride breaks up into 1 calcium ion plus 2 chloride ions. So therefore we get 3 particles, I is 3. The next constant, Kf, is the freezing point constant for water. And this is always going to be equal to negative 1.86 degrees Celsius per mole. And I'll describe what a mole is in a second. But notice how this Kf is negative. This means that the value of the entire equation will be negative because freezing point gets lowered by colligative properties. There's freezing point depression. So we need to subtract this, whatever we get from delta Tf, from the original freezing point. The lowercase m stands for molality. Now, note that this is molality, not molarity. And it's also a unit of concentration. And the formula for molality is moles solute divided by kilograms of solvent. So it's the number of moles of the solute divided by the mass of the solvent. Note that this is the solvent, not the entire solution. So if you dissolved salt in water, you would have a certain number of moles of salt divided by the mass of that water. For boiling point, the equation is very similar. This time, delta Tb, the change in boiling point, equals I, the Van Hoff factor, times Kb, the boiling point constant for water, times the molality of the solution. Kb always has the same value, and it's going to be 0.52 degrees Celsius per mole. So really the only difference between these two equations is the constant. This is the constant for boiling point. This is the constant for freezing point. The boiling point constant is positive because the boiling point increases. We add whatever we get here to the boiling point of water, which is 100 degrees Celsius. Let's look at a sample problem. So 10 grams of sodium chloride are added to 0.75 kilograms of water. What will the new freezing point be? Well, this is a freezing point depression, so we'll write the equation will be delta Tf equals I times Kf times the molality. So let's plug in what we know. Well, sodium chloride, when placed in water, splits into one sodium ion plus one chloride ion, which gives its I value to be 2. It breaks into 2 particles. Kf, we know it's a constant. Kf equals negative 1.86 degrees Celsius per mole. And the molality, well, we need moles of sodium chloride divided by kilograms of solvent. So let's solve for that. 10 grams sodium chloride over 1 times gram sodium chloride on the bottom, moles on top. Grams cancel. We get 1 mole is 58.45 grams to get 0.17 moles. So this is going to equal 0.17 moles of solute divided by 0.75 kilograms of solvent equals 0.23 mole. So now that we have all 3 values that we need, we can plug into the equation. So 2 times negative 1.86 times 0.23 will equal negative 0.86 degrees Celsius. That's going to be our change in temperature. So the question, though, is asking for what is the new freezing point of water. Well, water usually freezes at 0 degrees Celsius. So we're going to subtract the 0.86 because we've decreased our temperature by that much, and we'll end up with negative 0.86 degrees Celsius as our new freezing point. Notice how the freezing point doesn't change by a lot, even though we added 10 grams of sodium chloride, but there is an effect.